Hi everyone, welcome back for P3. In P1, we talked about some real numbers and their properties and some very basic algebraic concepts. And then in P2, we extended what we talked about for exponents in P1 to an entire section in P2. And now that we have a better grasp of what exponents are and how we can add, subtract, multiply, divide those things, we can now talk about polynomials. Well, before we talk about polynomials, we should talk about monomials. So monomials are single terms with a constant and a whole number power of x. So the general monomial would be a times x to the k. So we say a is the coefficient, x would be the variable, and k is the degree. K is also an exponent, but if we're talking about the monomial itself, k is the degree of the monomial. If k is not a whole number, it's not a monomial, period. So we're only going to talk about monomials or terms that have whole number powers. So if it's like 4/3 as a power or square root of 2 as a power, we don't classify it as a monomial. If the coefficient a equals 0, well, then we have 0 times x to the k, and 0 times anything is just 0. The monomial and the eventual polynomial that is equal to 0, we say has no degree. So it's not degree 0. You're going to see on the next slide that there's a difference between degree 0 and no degree. But for when a monomial equals 0, that specifically is the only monomial that has no degree. Otherwise, we would have degree 0 in some cases. So let's do some classification. Let's say we have 2x to the fifth. Well, the coefficient would be 2, and the degree would be 5. Okay, kind of straightforward. Negative 3x squared, the coefficient would be negative 3, and the degree would be 2. 8x, well, the coefficient's easy to tell that it's 8, but the degree is 1 because x to the 1 is x. So there's an imaginary power of 1 up here. No power written, we assume it's power 1 like we've done in the past couple sections. Negative 7, well, kind of easy to tell that the coefficient is negative 7, but a little less obvious what the degree is. Well, the degree in this case is going to be 0 because x to the 0 is 1. So imagine that there's an imaginary x to the 0 here that we just don't write because we never write x to the 0. Normally, we would say x to the 0 is 1. So there's an imaginary x to the 0 here. So you could take it that single constants are degree 0. And again, I want to note from the previous slide, this is different from no degree. No degree is the monomial 0. Degree 0 is any constants. So negative 7, 3, 5/2, and so on. X to the 12th, well, the coefficient is what's missing this time. There's an imaginary 1 out in front, right? 1 times anything is itself, so coefficient would just be 1. And the degree, 12. Negative x to the 4th, well, the coefficient would be negative 1, right? There's an imaginary 1 sitting between the negative sign and x to the 4th, and the degree would be 4. Okay? And again, just notice that all of these powers are whole numbers. We don't do anything that has a weird exponent, for example, like 4/3 or square root of 2, right? We only want whole number powers. So we can combine monomials in a couple different ways. So 2 or more monomials can be combined if they have the same degree, only when they have the same degree. For example, 2x to the 5th and 3x squared cannot be combined, but we could still write 2x to the 5th plus 3x squared, or 2x to the 5th minus 3x squared. So these are things that are okay to write, and we'll talk about these things in the next slide. But in terms of combining them, we can't do that. However, negative 3x to the 5th and 9x to the 5th can be combined in the following ways that we call combining like terms. So we're going to use this term a lot. Anything that is a like term is anything that has the same degree. So negative 3x to the 5th, 9x to the 5th, they have the same degree. We can combine them. Okay, so if we wanted to add these things, well, what we're doing is just adding the coefficients. So if I have negative 3x to the 5ths and 9x to the 5ths and I add them, I now have 6x to the 5ths. Okay, right? Negative 3 apples plus 9 apples, you now have 6 apples, except now those apples are just the degree term, x to the 5th. Subtraction functions the same way. -3 minus 9 this time. -3 minus 9 is -12. Okay? So now those things that we couldn't combine before, 2x to the 5th plus 3x squared or 2x to the 5th minus 3x squared, they are called polynomials. Okay? So a polynomial is a sum of monomials. Now, the general polynomial that we'll look at again when we get to chapter 3, but for now, just the general polynomial expression looks like this. Now, this is kind of daunting. It's okay. This says some coefficient x to some power, some coefficient times x to 1 power less, some coefficient times x to some power 2 less, and so on, all the way until we get to x squared, x to the 1, and the constant x to the 0 term. Okay, well, all of these separate things being added or subtracted together, we call them terms. The leading term is the term with the highest degree, and if you notice, well, this is n minus 1, which is going to be less than n minus 2 is less than n, so we write terms in descending power order, which means the highest power is going to be a sub n, x to the n. The highest power, n, is the degree of the polynomial. So whatever is the highest power that you see across the entire polynomial expression, that is the degree of the polynomial. And again, all of our terms must have whole number powers. And likewise, if something didn't have a whole number power, we would just say it's not a polynomial. A sub n minus 1, all the way down to a sub 0, those are all real number coefficients. So the coefficients can be anything, but again, the powers have to be whole numbers. The leading coefficient is the coefficient of the leading term. Well, leading term's right here. Coefficient of the leading term, a sub n. And we want to make sure a sub n does not equal 0. Well, if this coefficient equals 0, then 0 times this is just 0, which would make this the new leading term. So instead of this constant, well, let's make the leading term 0, so the leading term is just the next term. That doesn't make any sense. So leading term should make sure that that coefficient does not equal 0. Standard form, I mentioned it before, it's terms being written in descending power order, right? If this is the highest power, this is 1 power less, all the way down to our constant term. If all the coefficients are 0, well, then our polynomial would be 0 times x to the n plus 0 times x to the n minus 1, and so on. And all of these things, 0 times anything is 0. And again, 0 is the only polynomial slash monomial that has no degree. Not degree 0, no degree. Just to do a very brief example of classifying polynomials. So 5x squared minus 3x plus 1, the terms, each, all of the things that are being added or subtracted together. So 5x squared, negative 3x, and 1. The coefficients, well, just take the coefficients of each of the terms, 5, negative 3, and 1. And the degree is the highest power that we see in the entire polynomial. Highest power we see is 2. That's about it. Okay, well, we're very interested in doing operations on polynomials. So we're going to add, subtract, multiply, all sorts of stuff like that. So adding polynomials, if we wanted to add these two things right here, all we're going to do is combine like terms. So we have this polynomial plus this polynomial, and all we're going to do is group like terms together. So negative 4x cubed plus 6x cubed, we're going to pair those together. 5x squared and negative 2x squared, we're going to combine those together. 7x minus 8x, negative 2, and negative 5. Okay, well, negative 4x cubed plus 6x cubed, that's going to be 2x cubed. 5x squared minus 2x squared is going to be 3x squared. 7x minus 8x will be negative x. Negative 2 minus 5, negative 7. Okay, if you can jump from this line down to this line by just combining, in your head, that's totally fine. I'm just showing you what's happening, in that intermediate step. So don't feel like you have to do this. If it helps you, you should to combine and regroup, but this is the step I'm looking for. Okay, so adding, kind of straightforward. Now, when we are subtracting, subtracting is very similar, except what we're going to do is to get this back to addition and to make it look exactly like we just had on the previous slide, we're going to distribute this negative sign to each term here, right? We're doing 9x to the fourth minus 2x to the fourth minus 6x cubed minus negative 11x cubed. And you can already kind of hear that it's a little weird going on, right? So let's distribute a negative 1 to all 4 of these terms. 2x to the fourth will become negative 2x to the fourth. Negative 11x cubed will be positive 11x cubed minus 5x minus 3. And now let's group terms again. So 9x to the fourth, negative 2x to the fourth, negative 6x cubed, 11x cubed. Well, here, notice that we have a 4x squared, but we don't have an x squared term here. And that's okay. It just means there's nothing to combine with it. It's just going to stay itself. And likewise, we have a negative 5x here with no x term over here. And that's still okay. It just means negative 5x isn't going to change. Negative 1 minus 3. All right. 7x to the fourth. Negative, this will be 5x cubed. 4x squared is itself. Negative 5x is itself. And negative 4. Not too shabby. If we wanted to multiply polynomials, well, let's start with multiplying a monomial with a polynomial. And this is just like distribution. So we want to remember that x to the a times x to the b is adding the exponents. So let's multiply this monomial by polynomial right here. And what we're going to do is distribute 4x cubed to each term. Okay, we'll start there. Well, 4x cubed times 3x squared, this is something that we did in the previous section. 4 times 3 is 12, x to the third times x squared, x to the 3 plus 2, x to the fifth. 4 times negative 5, negative 20, x to the third times x, x to the fourth. 4 times 7, 28x cubed. That's multiplying, just using the product rule from last section. If we want to multiply a binomial with a binomial, so a binomial is a subgroup or subtype of polynomial where a binomial is just 2 terms. So a polynomial is any number of terms. A monomial is 1 term. Binomial is 2 terms. Okay, well, what we're going to do is introduce this acronym FOIL. And what foiling says is take the first terms in each binomial and multiply them, F. Then take the outer terms in each binomial and multiply them. Then take the inner terms and multiply them. Then take the last term in each binomial and multiply them. So you've heard this acronym before. You probably know what FOIL means, but anyway, let's do examples of this. So here we have x plus 2 times x minus 7, and foiling says multiply the first terms, f, x times x is x squared. Then multiply the outer terms, O, x times negative 7. Notice it's like the outer terms. Okay, x times negative 7 is just negative 7x. Then multiply the inner terms, I, 2 times x, right? They're the inner. Well, if these are the outer, then 2 and x are the inner. So multiply those together, we get 2x. And then multiply the last terms in each binomial. 2 is last, 7 is last, so 2 times negative 7, negative 14. And then we just need to combine like terms, negative 5x. There we go. And what you're going to see in the next section is how we can go back from x squared minus 5x minus 14 back to x plus 2x minus 7. But that's the next video. Another one, 2x plus 3 times x minus 1. First terms, 2x times x, 2x squared. 2x times negative 1, negative 2x. Inner, 3 times x, 3x. Last, 3 times negative 1, negative 3. And then just combine those inner terms. Negative 2x plus 3x is x. 3x minus 5 times 4x minus 6. 3x times 4x, 12x squared. 3x times negative 6, negative 18x. Negative 5 times 4x, negative 20x. Negative 5 times negative 6, positive 30. You are $18 in debt. You spend another 20. You are now $38 in debt. Okay, some special products that you will see over time that you could jump to if you so wanted to, but not so common. they're going to be a little bit more helpful when it comes to the next section, but still, we can introduce them here. If we have a plus b squared, so a sum being squared, well, a plus b squared is a plus b times a plus b, right? Something squared is itself multiplied by itself. Well, this is foiling. So a squared plus ab plus ba plus b squared, but ab and ba are the same thing. So a times b is the same as b times a. 2 times 3 is the same as 3 times 2. So ab plus ba is 2ab. Also 2ba, but 2ab looks a little bit nicer writing terms in alphabetical order. A minus b squared, so this is a difference squared. And same setup, except we got to be a little bit more careful. A squared minus ab minus ba, but plus b squared, right? Negative b times negative b is positive b squared. All right, well, negative this minus itself, negative 2ab. Difference of squares, a plus ba minus b. So difference of squares is what the final answer is going to be. Again, helpful in the next section. But in this case, a plus b, a minus b. A times a is a squared. A times negative b is negative ab. B times a is ba. B times negative b is negative b squared. And this time, notice these two things that are the same, but one is negative, one is positive, so they cancel out. So difference of squares comes from the fact that these two things squared are being subtracted. It's a difference of two things squared, difference of squares. Some more special products, a plus b cubed, a sum cubed, looks like this bad guy. You can practice that on your own. A minus b cubed is this bad guy right here. Sum of cubes, so this is not nearly as common. You're probably not going to remember how to do this one. But yeah, this would be a cubed plus b cubed if you were to expand it. A minus b times a squared plus ab plus b squared would be a cubed minus b cubed. So again, this is a sum of cubes. This is a difference of cubes. If you want to see where these come from, these are really good polynomial practice for you guys to work on. Multiplying some bigger things, right? So we had foiling, but what we can do now is multiply anything bigger. So what you might have noticed when we were foiling is that each term in one polynomial is going to each term in the next polynomial. So, right, that first term went to both the outer and the first term in foiling went to both the first and second terms in the second polynomial. And the second term in the first binomial went to each term in the outer part. It's making more sense saying it in my head, but I think you guys understand. So long story short, what we're going to do is make sure we do 4x squared times each part here and 3x times each part here. So in a sense, 4x squared times all this plus 3x times all of this. Okay? Well, what we can do here is now just distribute 4x squared to each term. And now this is just a series of multiplying together. Okay? 4x squared times x squared, 4x to the fourth. 4x squared times 2x, 4 times 2 is 8. X squared times x, x cubed, and so on. I think you guys are okay up to there. And now just combine some like terms. 8x cubed plus 3x cubed, 11x cubed, negative 12x squared plus x squared, negative 6x squared. So that's how we can FOIL, or FOIL on a grander scale. Just very briefly, let's talk about when we have multiple variables at play. So for terms with a constant and multiple variables, like 5x to the fourth y cubed, well, the constant is still the coefficient. So above this coefficient would still be 5. But the degree is a little different when it comes to multiple variables. Not as common, but still a little different. So the degree would be the sum of the powers of our variables. So that our degree in this term would be 4 plus 3, which is 7. We can't combine added or subtracted terms with different sets of variables, even if they have the same degree. If we want to combine them via addition or subtraction, they need to have the exact same set of variables with degrees. So for example, 5x cubed and 2y cubed, we can't simplify that because x cubed and y cubed are not the same set of variables and powers. However, 5x cubed and 2x cubed can be, 5y cubed and 2y cubed can both be simplified. But terms with the same set of variables can be combined. So 5x to the fourth y cubed plus 12, x to the fourth y cubed, right? They have the exact same set of variables, so we are able to combine. Well, 5 apples plus 12 apples is 17 apples. But again, those apples are x to the fourth y cubes. But x to the fourth y cubed, x squared y to the seventh, different set of variables, we can't combine them. So when we're multiplying terms with different variables, we just treat those variables separately, right? Think about when we've been multiplying, 4x times 2x squared. We multiplied the constants together and we multiplied the x's together. And same thing here. We're just going to multiply different variables separately. So x times y is just xy. X to the 6th, y to the 4th is just x to the 6th, y to the 4th. X squared y cubed times x to the 7th, y to the 9th. All this is multiply the x's together, multiply the y's together, and we get that. So doing one more example, if we're just expanding a multiple variable polynomial. So 2x plus 3y squared says 2x plus 3y times 2x plus 3y. Okay, 2x times 2x, 4x squared. 2x times 3y, 6xy. 3y times 2x, 6yx. 3y times 3y, 9y squared. Again, xy is the same as yx, so we get 12xy. Same set of variables, we can combine them. 6 apples plus 6 apples gives us 12 apples. Okay, and just like that, that's the end of P3. So in P4, what we're going to do is factoring polynomials. So going from expanded polynomials back to nice, pretty ones, nice, pretty factored ones. So I will see you in P4.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.